Hey, aloha, and welcome to Stan the Energy Man here on ThinkTech Hawaii. Stan Osserman coming to you live and direct from beautiful Kailua. In fact, I would say this is probably like the first day of summer. There's hardly a cloud in the sky, just enough clouds around the mountains to make them interesting. Light trade winds, about 75 degrees or so on the temperature. This is the kind of day you want to just get away from the mainland and come visit Hawaii. So pack your bags, get your coronavirus vaccine done, and jump on a flight, come on out to Hawaii and have a good vacation. So anyway, today's show is called You Can't Spell Oil Without Hydrogen. And I had a long discussion with the producer on how that makes a lot of sense because she said it didn't make any sense. So I'll explain what I'm saying when you can't spell oil, or you can't spell propane, or you can't spell any other fuel without hydrogen. And that's if you're a chemist. So if you're a chemist and you're building a model to explain the molecular composite of um, a a molecule of a fuel like gasoline or diesel fuel or jet fuel or propane or natural gas, you start off with atoms. So hydrogen is an atom, but most of those other fuels are actually compounds. They're molecules. They're atoms arranged in a certain way so that they do what they do in unique ways. So whenever you try and make a hydrocarbon fuel, you can't do it without hydrogen. So if you're a chemist and you're making a model, like CH4, CH4 is carbon and 4 hydrogen atoms. So anytime you make methane or propane, or you've got to have hydrogen, otherwise the chemist can't put it all together. So that's what I meant by you can't spell oil without hydrogen. Well, now that I've done the whole show, see you next week. No, just kidding. I wanted to talk a little bit about what makes hydrogen so important right now. Why we should really be focused on hydrogen as a replacement to most of our fuels. And I'd say fossil fuels, but I really kind of mean even like wood, carbon, other fuels besides liquid fuels. And we're going to get into that. But a little trivia. You've heard of hydrocarbon fuels, and you go, well, hydro kind of sounds like water, but they don't have water in them, so why do they call them hydrocarbons? And then you have hydroelectric dams, and it's like, well, they make electricity, and they got water running through them, so I can figure that out. But how come, what's with hydrogen? I mean, it sounds like it's water. Well, when the early scientists started, really getting into modern chemistry and physics and things, and they discovered the atom and they started naming things. Hydrogen is the first element, the first atom on the periodic chart of elements. And so hydrogen, when they first started, playing with it, learning about it, they discovered that when you took hydrogen and you burned it in the presence of oxygen, it turned into water. So hydrogen is actually comes from the Greek language, with hydro meaning water and gen like in generation. So hydrogen is the atom that generates water. It's what you make water from. So the word hydrogen is water maker, and it comes from Greek. The early modern scientists used a lot of Greek and Latin to describe what they were seeing or what they were discovering. And so that's how hydrogen got its name from the Greek as water maker. And that's because hydrogen, literally, if you burn it, it turns into heat and water. That's it. Nothing else. And that's really important for the discussion today. And I'll explain it as we go along. But let me see. Another important thing about hydrogen along these lines is when you're trying to store energy, there's lots of ways to store energy. The most common way that we think about electrical energy being stored is in batteries. But of course, we use oil in transportation, gasoline and diesel fuel and jet fuel for airplanes. They're all liquids and they're all fuels, but they all store energy. And all of those things, whether they're batteries or fuels, and they store energy, they have to have the chemistry to do that. And as we explained earlier, hydrogen, the most plentiful element not on Earth, but in the universe, is found everywhere, and it's almost always attached to something else. So we oftentimes think about, well, how do you compare hydrogen and hydrogen fuels to like electric batteries? And I have a pocket reference book that I use for a lot of things, mostly converting weights and measures and things like that. But one day I was going through it and I stumbled across a chart that talked about batteries. And interestingly enough, it made me understand the term fuel cell. Um, and the reason I say that in the context of batteries is I could never understand why they called the engine that you put hydrogen in to generate electricity a fuel cell. It just didn't seem to make sense to me. But when I found this chart in this pocket reference, it was comparing energy storage values and it was using amp hours per kilogram. In other words, how many amp hours of electricity you get out of a kilogram of weight using that chemistry. So the reason it came up with fuel cells is because the fuel cell is listed under batteries. And I'm scratching my head going, well, yeah, it has a cathode, it has an anode, and it makes electricity. I guess that's a lot like a battery. So if you think about it, you have all different kind of batteries and we categorize them. You have wet cell batteries, the kind that's in your car, a 12-volt battery that has lead acid, lead partitions, lead cathodes and anodes, and it has an electrolyte, which is hydrochloric acid, and it can store up energy, electrons, and then release them. So you have wet cell batteries. And then you have things like nickel metal hydride or nickel cadmium or alkaline batteries. Those are dry cell batteries. They're chemicals inside, but they don't have a liquid electrolyte. And then you even have things like flow batteries, which are huge big vats of liquid that have metal plates and stuff in there, kind of like a wet cell battery, but they actually have circulation going around it. And it's an interesting chemistry. I've never had much luck using flow batteries. I've tried several of them and worked with people that have tried a bunch of them, and they just don't seem to deliver. They're actually noisy, for one thing. But then there's the fuel cell, the lowly hydrogen fuel cell, which never gets any press, never gets any attention, but it's a self-charging battery. You put oxygen in one side, you put hydrogen in the other side, and it makes heat, electricity, and water. And that's what you're trying to do, make electricity. So the fuel cell gets categorized, and not just the hydrogen fuel cell, there's solid oxide fuel cells, there's several different kinds of fuel cells that end up taking a fuel and turning it into electricity. So let me compare a couple for you. And I use this a lot because it's important when we get into a discussion of batteries versus hydrogen for energy storage. Your typical car battery has ability to store about 54 amp hours per kilogram of weight, your lead acid battery. So it can do 54 amp hours of energy for every kilogram of weight. Then you've got lithium ion batteries, the ones we use in our cell phones, the one we use in our Makita drills, or our DeWalt and um, Milwaukee drills that are so great because you can go do hours of work and you don't have to have a cord tied to your drill and stuff. So the lithium ion chemistry is about 685, much better than the heavy lead acid batteries, and much lighter too, by the way. Nickel cadmium, the batteries that we used to replace the old original Rayovac batteries and stuff, they're about 165 amp hours per kilogram. So we've got, and there's, oh, by the way, there's a thing called an ammonia battery, and it actually can run 1400 amp hours per kilogram. So you've got your lead acid at 54 amp hours per kilogram. You've got your nickel cadmium at 165 amp hours per kilogram. You got lithium ion at 685 amp hours per kilogram. And you got ammonia batteries at 1400 amp hours per kilogram. Well, once you get into the fuel cell range of batteries, there's a chemical called hydrazine. And hydrazine is, and the Air Force is very familiar with hydrazine. They use hydrazine as the battery storage for emergency flight controls and things on the F-16 fighter jet. So it's a really important mission because the F-16 only has one engine. And if the engine goes out, you don't have a whole lot of battery time on a regular battery. So they have hydrazine that gives them much more energy. A hydrogen battery or hydrogen fuel cell gives you about 2100 amp hours per kilogram. So all of these guys are really good, and hydrazine is one of the better ones at 2100 amp hours per kilogram compared to the other batteries. That's like almost 4 times, or at least 3.5 times better than lithium ion. But guess how much just plain old hydrogen is in a fuel cell? 26,000 amp hours per kilogram. In other words, by weight, you just cannot beat pure hydrogen. And so that chart was a real eye opener for me. Number one, to really explain what a fuel cell was and why it was called a fuel cell when I was first learning about hydrogen. But it also explains that by weight, you just can't get more energy out of anything like you can hydrogen that we work with. Now, this kind of explains a couple of things. When you want to get a lot of hydrogen um, density, like hydrogen, the real scientific term is very fluffy. It's very light. It floats. It's 14 times lighter than air. So if you want to collect a whole bunch of hydrogen, unless you happen to be making a dirigible or something, if you want to store the hydrogen in a container, you got to compress it, put it under pressure and squeeze it all down to fit into a container. Or you can get it super, 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 super cold, like 250 degrees Celsius minus, and that gets it down to where it'll be a liquid. So when you have a rocket ship and you want a really dense fuel, one of the most common ones that NASA's used for years is liquid hydrogen. And I think they also put hydrogen peroxide in 2 separate containers. And when you mix them together, you have a very, very volatile rocket fuel. So it gives you incredible amount of energy. And if you have it frozen down at that minus 250 C, you get a pretty dense, high energy liquid to make a rocket fuel out of. But I just heard that Elon Musk doesn't use hydrogen for liquid rocket fuel. At least not, he doesn't think so because he doesn't like hydrogen. But he does use ammonia. And ammonia is NH4, NH3, excuse me, NH3. So it's one atom of nitrogen from the air. Air is about 75% nitrogen, and 3 atoms of hydrogen. And when you have NH3, you have a liquid that's basically 3 parts hydrogen and 1 part nitrogen. And he uses ammonia as the fuel in his rockets. That's the chemistry in his rockets. So when you do anything with transportation, the lighter the fuel, the more range and the more mileage you get. You don't have to lift as much of weight in fuel. So when it comes to transportation, you always hear me say, when it comes to transportation, it's all about weight. And that's because the more fuel you're carrying around, the more weight in fuel you're carrying around, the less efficient your system is, your mobility is. So for example, when I start talking about batteries versus hydrogen, if you have a Tesla with quite literally a ton of batteries in it, and a hydrogen fuel cell car like a Toyota Mirai, which has fairly small battery and a fuel cell and about 5 kilograms of hydrogen. The weight is dramatically different. And therefore, the Tesla is using a lot of its energy to move its batteries around, because you've only got 3 or 4 people in the car, but you've got tons, literally a ton of batteries in there to move around. Where in the fuel cell vehicle, you have maybe 800 pounds instead of 2,000 pounds. You have much, much less weight to move around. Plus, the fuel cell and even the traction battery that goes in a Mirai is all below you, just like in a Tesla, the batteries are underneath you. So it makes the center of gravity on that vehicle really low, keeps it tight to the road, and helps handling quite a bit. So when it comes to transportation, it's all about weight. And so no matter whether you're talking cars and trucks, or trains, or boats, or ships, or rockets, and airplanes, you just can't beat hydrogen for the energy storage that you have when you have such a lightweight fuel or a lightweight energy storage component in your system. Now, in all fairness, hydrogen has a lot of energy in it. And one thing I got to say, and this isn't to say, one is better than the other in terms of all around performance, but when you have energy stored up, whether it's in a battery, whether it's in behind a dam in water, stored up water, whether it's a boulder at the top of a hill, whether it's gasoline in a can or a tank, whether it's propane in a tank, you have stored energy. And stored energy has got to be handled with respect, no matter what kind of energy it is. And so therefore, when you look at hydrogen, and you really have to respect how much energy it has, you do have to handle it carefully. And there's a lot of studies have been done over the last 100 years on how to handle hydrogen properly and safely. And so we've pretty much got it down with specialized tanks to store hydrogen at pressure, and safety valves and setbacks and all kinds of things. And industry has really, really gotten just as good with hydrogen safety as it has with gasoline safety and propane safety. Does that mean you can't have an accident with it, or that it can't be you can't make mistakes with it? No, you have to be paying attention anytime you're using stored energy. You've got to have the safety in place. You've got to follow the rules to the T, or you can have some serious problems. So, speaking of which, when I was doing some homework on for another project, I decided to look at a video produced by a local TV station. I wish we could show you the video, but with all the copyright stuff we have to go through to get permission to show it, I'm just gonna have to explain it to you. But this was a local TV science show put on by a local station, and they were trying to show the energy and how hydrogen reacts. So what they did was they filled 3 balloons. One balloon had oxygen in it, one balloon had hydrogen in it, and one balloon had hydrogen and oxygen in it mixed up. So the first thing they did was they took a stick with a wick at the end and lit it, and they held it under the oxygen balloon. And as soon as the rubber burned through with the flame from the wick, the balloon burst and it just popped like a regular balloon would pop. Then they did the same thing with the hydrogen balloon. But this time, when the fire burned through the skin of the balloon and all the hydrogen escaped, you heard the pop of the balloon, and then you also saw a big orange and blue fireball that was about 6 times bigger than the balloon, and it just lasted a second, and it made a whooshing kind of flame sound. So I was kind of interested to see what they were going to do with the balloon full of hydrogen and oxygen mixed together. So I'm thinking, that's a lot of hydrogen, a lot of oxygen. So I hope they're not going to try and light that balloon off. They might just wreck their studio a little bit. So what they did was they filled a tray full of soapy water. And in this tray, they had this young lady soak her hands in the water to get them wet up to just above her wrist, and then he took the hydrogen oxygen balloon and they had a tube and they let a bunch of the hydrogen oxygen into the water to make bubbles. And of course, it was like a bubble blowing solution, so it made a whole bunch of bubbles. And the young lady was told to scoop up no water, just scoop up some of the bubbles. And she had her two hands together, and she scooped up about half of a volleyball of bubbles in her hand. And the guy running the experiment basically took a lighter and touched it to the bubbles. I'm going to back up just a second. Before they did all this, they put on earmuffs. And so the lady doing the bubble holding was a little bit worried about what was going to happen. And so when they actually lit the handful of bubbles on fire, there was a rather large explosion. I mean, it was an attention-getting explosion. It really, you know, it's a good thing they had the hearing protection on. When you have hydrogen as a fuel, a pure hydrogen like they do in cars, it's not flammable. It's contained in a tank, and it won't burn until it gets out and starts mixing with air. But when you take oxygen, which is actually kind of dangerous on its own as an oxidizer, and you mix it with hydrogen as a very high energy density fuel, and you have the two of them together, it doesn't take a whole lot to make a really fast burning, attention getting boom. So you do have to be careful with hydrogen. And that video got my attention because literally the balloons that they blew up with oxygen and hydrogen were regular sized balloons. And you look at them and they didn't really make a big noise or a big bang or anything. But holy mackerel, just a little handful of bubbles mixed with oxygen and hydrogen got everybody's attention in that room. So by definition, whenever you're storing that much energy, you got to be safe and you've got to handle it properly. And you have to understand what you're dealing with. So the technology today is to make, or the aim of the technology today is to make hydrogen fueling and hydrogen vehicles what we used to call pilot proof, or you can't mess it up no matter how hard you try. To put enough redundant safety systems in to make things really safe. And they have. The storage tanks are very safe. They can't be ruptured. They have safety valves on them. They have impact resistant valves on them that when you have an impact in a car, if it's severe enough and it looks like it might have caused some severe damage, it'll actually release all the hydrogen from the tank. And it's very directional. It goes out a vent instead of cooling underneath the car, and it's 14 times lighter in air, so it goes right up in the sky and makes clouds. So when you think about hydrogen safety, you got to be confident and comfortable, just like you are in your car. You're dealing with gasoline in your car right now, and it's pretty dangerous itself. There's a lot of gasoline stations that have fires at them when people don't pay attention, like fueling a can in the back of your pickup truck, where you don't have good grounding and you can actually get static electricity starting a fire in your truck. You just got to follow some regular safety precautions. So what is the main point that I wanted to get to today? And I started off by talking about hydrogen being an atom and making compounds and molecules, and oil and everything has all these other things in it, carbon, nitrogen, all kinds of stuff in it. That what happens to them when you burn them in an engine, or you burn them in a coal plant, or you burn them in an electric plant to make electricity? Well, you're getting most of the energy from the hydrogen piece, and all the rest of the stuff just goes up in the air as pollution. It goes up in the air as carbon dioxide, carbon monoxide, NOx, all kinds of things that we don't want in the air. Not just greenhouse gases, but all kind of pollutants that we don't want in the air, particulates and everything. So why is it that we still want to be doing that? It just doesn't make sense. Doesn't it make more sense to use a piece of that compound or the piece of that molecule that has all the energy in it for your energy storage and not deal with all the carbon and the other things. That's why we're looking at hydrogen so carefully as energy storage. It's non-toxic. It's 14 times lighter than air. It's it's very efficient, and it doesn't produce any pollutants when you burn it. It just makes water. So back in the early caveman days, man was so proud of himself because he discovered fire and he was burning trees. And then he found out that if you wanted to have it even better, you could make charcoal and you could have nice hot fires with charcoal, but you're still burning trees. Um, but burning trees, once you burn the tree, it's not much good for anything else. Whereas you could build a house or all kind of things, boats with trees, and they would last for hundreds of years. But when you burn it, it's gone in a few minutes. Same with oil. We could take oil and make all kind of durable plastics, all kinds of really great things out of oil. But instead, we're burning it and throwing the rubbish parts of it into the air. When you're burning hydrogen, just getting water. So why would you take compounds that are full of all kinds of other unwanted byproducts and burn it to make energy? Not only does it waste the environment and pollute the environment, it's a waste of money. Just think if you had a barrel of oil and you could make, you know, hundreds of durable plastic goods from that barrel of oil, doesn't that make more sense than burning it in a tank of gas, making a couple gallons of gasoline and burning it, and then and it's nothing. It just doesn't make any economic sense to keep burning. It's like burning money. Why would you burn money? It just doesn't make sense. So instead of burning these compounds, we should be using hydrogen to make our energy, store our energy, and bring it back around as electricity in a fuel cell rather than burning the money, burning the compounds that we have, the fuel and things like that, and making pollution and basically wasting that money. So, just a quick recap. Hydrogen is the purest fuel available. When you burn it, it just makes water. When you use it in a fuel cell, it makes water, electricity, and heat. It's so basic. You don't get any pollution. You don't get anything toxic from it. In fact, even if you have a leak of hydrogen at your station and a whole bunch of hydrogen escapes into the air, there's no big puddle of fuel on the ground to catch on fire. And the hydrogen that escapes eventually turns back into clouds and makes rain. So, why should we deal with all the other stuff that's not important for energy storage, not important for our needs? What we need is energy. Why don't we just stick with the basics? And 14 times lighter than air, hydrogen is awesome on the transportation side, and it's just as awesome on the grid side. Because if you do the math and figure out how many batteries you need for a gigawatt worth of electricity and compare it to how much energy you could store in hydrogen, it's about a quarter of the cost of those batteries. And we're not even beginning to talk about the combustibility of the batteries, the where they're from, the sourcing of the materials, the cobalt, the lithium, how it's harvested, where we get it from, who controls those resources for national security, all those things. Every country on the planet has hydrogen. Trust me. If they didn't have hydrogen, they couldn't water their plants. So we know they got to have some kind of water around them. And hydrogen, you can make it right from water in an electrolyzer. So, long discussion. Hope you can stick with me. You didn't lose anybody at the first, how do you spell oil without hydrogen? But my point is, there's much better uses for oil and oil-based products and compounds than burning them. And hydrogen, whether you burn it or whether you use it in a fuel cell, it's clean, it's great, it's economical. And if you use it on the grid and you store your energy in hydrogen, It actually helps you stabilize the grid and gives you oxygen while you're making your hydrogen. You can use the oxygen in hospitals and for welding and things like that. And then when you use the hydrogen back in your fuel cell to give you back your energy, all you're making is water, heat, and electricity. It just doesn't get any simpler than that. So there's my hydrogen primer from nuts to cavemen to modern rocket scientists. And I still think hydrogen is the best way to go. Just got to handle it safely because it does have a lot of energy in it. So anyway, that is going to do it for today's Stan the Energy Man here at ThinkTech Hawaii. Thanks for joining me, and thanks for being here at ThinkTech. If you can log on to ThinkTech's website and make a donation to help some good shows happen, you got Lillian's vegan cooking, you've got Law of the Sea, you've got all kind of great shows here on ThinkTech Hawaii you could be supporting. So please log on and contribute if you can. So until next Tuesday, this is Stan the Energy Man signing off. Aloha.